In this project, we examined the thermal properties of a polyester jacket and a cotton long-sleeve shirt. The result, while fairly obvious, the jacket being the better insulator, explain how heat transfers work. Thermal radiation is the transfer of heat through electromagnetic waves and without a medium. The Stefan-Boltzmann equation is used to calculate the amount of power radiated by a given body. A perfect black body or radiator absorbs all of the possible radiation that it comes in contact with. The sigma-Stein or Stefan-Boltzmann constant represents this perfect black body in the equation. Thermal conductivity is the rate at which an object allows heat to transfer from one surface to another. This type of heat transfer is called conduction, and it involves two objects coming in contact with each other and exchanging kinetic energy through their particles. This equation represents thermal conductivity, and it is set up to solve for the coefficient of thermal conductivity of a given substance. Newton's cooling law surrounds the differences in temperature and how an object's temperature is affected by its surroundings. The cooling equation stated here can be used to find an object's temperature at any given point during the duration of a heat transfer where the object is losing heat. The graph here represents a cooling curve of a polyester jacket and a cotton shirt. The flat line represents the thermal equilibrium, a temperature which the objects will not become lower than because the surrounding temperature is the flat line. As an object is heated, its particles gain kinetic energy, and each particle takes up more space as it vibrates more. This increase of space and vibration of particles causes the object to expand on a larger level. This expansion is represented by the linear thermal expansion equation shown here. Some materials, however, particularly the ones studied in this paper, shrink when their temperature is increased. As seen here, the polyester tie and cotton string both shrank under increased temperature, originally being 30 centimeters long and shrinking to 29 and 26 centimeters, thus causing negative thermal expansion and making both materials' coefficients of thermal expansion negative.